Okay, let's get started. Let's try to solve this one. Zoom again. Let's send this link to the chat. The good news is that we only has at most 16 in the board and 5 in the hand. So the size of this problem is really small. That's perfect. So that's usually a sign of backtracking, right? Because we can we are satisfied with the complexity of 2 to the n, right? 2 to the power of n. And we can shoot any ball to the board at any place, right? We can change the orders of the balls in our hand. And let's see. So basically, we are going to search each every of the possibilities, right? And we are going to store all of those status we have searched. And the status can be represented as the board and the balls in our hand, right? So for the initial status, it is clearly the original board and the number of balls in our hand. So we have 4 kinds of balls, R, Y. Actually, we can just use 5 dimensions, and the first dimension is a string, right? The string represents the current board, and the second dimension is the number of red balls in our hand, and the third dimension is the yellow balls in our hand, and so as B and G, right? And the white. This is our initial status. And when we decrease one of the numbers by 1, that means we shoot a ball to the board. And we can shoot this ball in any of the places, right? Do we want to use greedy and only shoot a ball to a place where we have 2 or more consecutive the same balls? No or yes? Let me see. Is there a possibility that the optimal option is for us to shoot a R ball at this place instead of this place? I think that is not the case, right? If we shoot a ball, we can actually change the form of this board to something like this. Right, so that we have 1 white balls and then 2 red balls, 2 black balls, blue balls actually, and 1 white ball, right? And when we throw a ball into the board, we have to choose the same color as that ball we want to throw, right? And in this case, if we decrease the R by 1, then we are going to shoot the ball here and increase the counter of R by 1. And we are going to check the shrinking status because here we are going to shrink the board, right? And I think that is pretty much how we solve this problem, right? Let's see. So what is my note there? Backtrack. Try to remove one of the ball at each run. Yep. Need to shrink for each run. Right. So here is the solution. Let's take a look. It's quite long. Right, this solution is quite long. Sort hand string so that I easily know if there are at least 2 balls with the same color in hand to eliminate a single ball on board. Okay. Here is where he does the search, right? And he is going to search by B and H. H is a hand, and B is the board. And each time he is going to pick up a ball in the hand. He will try each ball in his hand, right? Okay. So here is J is where he put the new ball in the board. And here is after you put a new ball in the board, he shrink the board, right? And there is a possibility that it might shrink multiple times. And we need to remove the ball from the hand. And we recursively search for the next state, right? Okay, I guess that's a typical backtracking problem. So I will stop here. I think that we just need to get a glimpse of the solution, and that's it. And hopefully we can solve this problem during the interview, right? Okay, let's go to the next problem. So again, okay, so this problem is a typical memorial. Is that memorial? Memorial search. I don't actually remember the name of the technique. Memorial search. Memory status. No. It's a memory search. Memorize this backtracking. So basically what we're going to do is to search all the states. The states is composed by the position of the cat and also the position of the mouse. And each state we only search once, right? And if the next move is the cat will search for will choose the next state where that state has a cat's win condition. And if that state has a mouse win condition, the cat will never choose it, right? So that is how we solve this problem. Okay, let's move on. Here we go. Disconnect island. So not many options we have. We can either confirm that the island is already disconnected, or we can remove one of the piece from the island and check if the island is disconnected. If both of the above are not true, it tells us that we can make the island disconnected by remove two pieces, right? Because if the island is not disconnected, it must have a top left corner, and we can simply remove two pieces, this one and this one, to make the top left corner disconnected, right? Okay, easy one. Stacking cubicles. This one is very hard. So basically what we are going to do is to sort the lengths, all three lengths of the cubicles, and then run a CIS algorithm, right? CIS is, LIS is longest increasing subsequence, right? Is the time complexity is n log n, right? And let's move on. So, whoops, we closed the Excel sheet. Unfortunately, let's scroll down about 221, right? Okay, divide chocolate. So you have one chocolate bar, and you need to make sure the minimal sweetness is maximal, right? So basically we will binary search the minimal sweetness and greedily make up those bars with the minimal sweetness, right? And to see if we can find enough number of bars that all of them satisfy the minimal sweetness. Cool, easy one. This one is also easy. So just a few options to make the lines cross themselves. For example, if this is the first line, then it can cross itself like this. This is the first, this is the second, third, fourth, right? So line 1 can cross line 4. And another option is 1, 2, 3, 4, 5. Line 1 cross with line 5, right? And another one, 1, 2, 3, 4, 5, 6. Line 1 cross with 6, right? We just need to check all the three options. And let's say for line 1 cross with 7. 1, 2, 3, 4, 5, 7, 8. This means line 2 cross with 8. That is the same with line 1 cross with 7. Wait, 1, 2, 3, 4, 5, 6, 7. Line 2 cross with 7, that is line 1 cross with 6. We already have that condition, right? So we don't actually need to check 2 cross with 7, right? So that's it, easy. And nth magical number, what is that? Okay. So a positive integer is magical if it is divisible by either a or b, right? And we need to return the nth magical number. So the magic number will look like this. It can have 1a as factor and 2a as factors and 3a as factors, right? And 1b as factors, 2b as factors, 3b as factors, right? And actually it can have 0 also, right? And this one is not magical. Let's say if a equals to 2 and b equals to 3, so that if we have a 1, 2, then the magical number is 2. If we have 1, 3, and 3, if we have both, then it's 6, right? We're going to have a two-dimensional table like this, and right, so basically in each row the next element will be 3 times more than the previous element, and in each column the next element will be 2 times more than the previous element. And let me see. Does this table contains all the magical numbers? Let me see. Ten. is a magical number, right? But 10 is not in this table. Okay, then this table is not very useful. No, 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 this cannot be solved by two-D sorted array. Interesting. First, we made a wrong note here. Second, this solution seems pretty smart. So basically what it does is to check a number to see how many magical numbers that are less or equal than x. And the x is your binary search target. How many magical numbers are less than x? How many? Okay, so basically we can divide that number by a, and that is the number of magical numbers divisible by a, and also divide that x by b to see how many numbers are divisible by b. And he's going to minus the total of that two numbers by the number of numbers that are both divisible by A and B. Hmm. Okay, so to calculate the third number, he used the x to divide by the largest common multiplier of A and B. Oh, that is smart. Okay. Whew, that was intense. Okay, great solution. So he used a binary search X and find out how many magical numbers smaller or equal to X. And to calculate that number, he used to S divide by A plus S divided by B minus X divided by LCM. Oh, cool. Okay, let's move on. Minimal 1-bit operation to make integers 0. Given an integer n, you must transform it into 0 using the following operations any number of times. Change the rightmost 0 in the binary representation of n. Change the ith bit in the binary representation of n if the I minus 1 bit is set to 1 and the I minus 2 through 0 bits are set to 0. Okay. Return the minimum number of operations to transform n into 0. So that is a typical memorized search problem, right? Let's see how many digits are there. At most 20 digits, right? Let's confirm that. 2 to the power of 20. So 2 to the power of 30. Yeah, that's it. 10 to the power of 9 equals to 2 to the power of 30. That means we're going to have 30 digits at most. And do we want to search every each of the states? So each state is one of the binary representation along the way, right? So we can use BFS Let's take another look at the second operation. So basically, it has something like this. I split the binary representation of n. If m, so this guy is set to 1, and this guy is the target, and all the following digits are 0. In this case, you can change this guy to 0, and then what you're gonna do, you can change this guy to 1, and then you can change this guy to 1, and then you can change this guy to 0, and then you can change this guy to 1, and you can change this guy to 1 again. Okay, I see what you mean. So basically, we are going to have a binary like this, and our goal is first to turn the leftmost digit into 0. In order to do that, we have to change all the digits. In order to do that, we first need to change the number at the right side of that target to 1, right? And then we need to change all the rest of the digits to 0, right? Is that possible? So we need to have a function saying that the target and the current status. Current status is just the binary, and if the target is 0, so we are going to have a function doing to 0, right? And to 0, what to 0 does is calculate the number of steps to convert current state to a state where all the digits to the right of the position are changed to 0, right? And after we done that, we are going to change the Mm, okay. So before that, we need to have another function to change a specific digit, the a digit from 0 to 1, right? Digit to 1. And this is the current status. And the pose is the position of the target digit, right? And how are we going to change that digit to 1? So in order to do that, we need to change the digits to the right of the position to 1. And then we are going to change all the rest of the digits to 0. Right? And that's it. So what about to 0? How are we going to change all the stuffs to 0? So what we are going to do is change, let me see. Okay, so if we want to change all the digits to 0, we need to change from left, change all the digits from left to right, from position to 0, to make sure each of the digits are 0, right? And we are going to have a function called digit to 0, right? And the way we are going to do that is to first check the next digit. If the next digit is, we need to make sure the next digit is 1, right? And make sure the rest of the digits are 0, right? That is a recursive method being used. So I guess that's it. Is that what we want? Or one space. Then – Let's see how many zeros is here. Yep. So basically, if we want to change this first digits to 0, we need to change the second digit to 1 and change all the rest of the digits to 0, right? Hmm. This observation is quite essential. I assume he just get this observation by observing, right? I mean, by read the examples. This can be easily this can be easily proved. I highly doubt it. Yep, exactly. is using recursive here, and he's also using recursive. And the way they use recursive is kind of interesting because the way I do the recursive is that I implement two recursive functions and they call each other. And his way is to calculate the total number of steps to change a number to a power of 2. Why it takes 4 operations? For this guy become this guy. Okay. They use minus. Since the change are bidirectional, so if it can change from one number to another number by x steps, then it can change it back by x steps. That is obvious, right? And from observation, he tells that if you want to change a digit at a certain position, the number of changes you need to make is 2 to the power of that position minus 1. in this case is 15. And this problem is hard. This is actually making sense. Okay, so basically his idea is doing it from bottom to top. So let's say initially we have 0, then the option operation 2 becomes if we want to change a digit at position uh, x, then we need to wait. Let's re-experience the steps. So when we change 0, first change the first digit to 1. Then now we can change the second digit to 1, 1. Then change the last digit to 1, 0. Then we can change the third digit. Right? Then we're going to change then then okay. So basically each time we move up for a digit, we're going to traverse all of those digits in between. And the 0, 0, 1 will always be the last number you encounter, so that your target number is always before the last number, which is ending with zeros. So that is why they have a minus sign here. And here is the steps you reach this state. So his idea is that you change 0 to the target. This is the number to the power of 2. And this is your target. And what you will do is that you reach to the number to the power of 2 first, then you go back by minus it at the number of the reduced problem. Interesting. Oh, this is very hard to understand actually. At least I found it difficult for me to understand. That is quite challenging. I feel like I need a break. I'm a little bit tired. memorize the DP is clearly not the case. Yeah, this one is actually much more easier to understand, and it is close to my original thought. So basically, if we want to change a number to all zeros, we are going to first check if the first bit is 1. If it is, we are going to transform the first bit to 0. That means we are going to change the next bit substring to 100 format and plus 1, right? And that is how we flip the first bit. After we flip the first bit, we are going to continue the subproblem, right, by flip the rest of the bits. And this function is to turn the number into the format of 1000, right? And what it does is that okay. Breaks into two steps. First, transform the right substring into 1000 format. Then you have the second operation condition, and you can flip the first bit, then transform the rest of bit to 0. Alright, that makes sense, but it's quite longer than the previous solution. Oh, this solution is brilliant, but quite hard to understand. Oh, okay, this one is hard. Easy to understand. Easy to implement. Tough one. Let's move on. I'm a little bit tired. Let's see, how long did we broadcast? Almost 2 hours. Oh, 1 hour and 20 minutes. Okay. So let's keep going. All right, keep the momentum. Our goal is 230. All right. The constraint, the data size is small, so can we try all the combinations of words? So we have 14 words. That's okay to try all of those combinations, right? For each combination, we're going to calculate the maximum score. That is easy. Yeah, we can try all combinations. Huh. Okay. Cool. So each round is trying to put another word into the set. And in each round, he will try to add a word or not to add a word. And if it add a word, he can check if he can actually add that word, because you may be short of characters. And if you can add that word, he will calculate the gain by adding that word. Cool. And he will pick the better one of these two options. And in each iteration, he will keep track of the score. I'm a little bit confused how he actually used the score. Oh, so I see. So the score table is actually one score for each of the characters, right? Okay. So it is not possible that two letters actually have two different scores, right? Okay, that is great. So here we have 26 score letters. Okay, that explains. Okay. Backtrack. Search all combinations in each round. Add or ignore one word. If we add, we calculate the gain, and if we check if it is valid. Okay, great. That's pretty good. Unqueen say unqueen should be the easy backtrack, right? So dinner plates. So you have an infinite number of stacks arranging in a row and numbered from 0. Each of the stack has the same maximal capacity. Implement the dinner plate class. Initialize the object with maximal capacity of the stacks. average watch time is quite long, guys. Unfortunately, there is no one watching right now. Sip some water, cheer up my spirit. This straw is actually good. I'm very much addicted to the straw. It's a hard straw. If you are used to use softer straws, the hard straw will kick your teeth every now and then. But if you get used to it, the hard straw, it actually feels good. Oh my god, I'm so tired, but I need to keep going because my goal is to reach 230. Oh, why it is so hard? I have learned these problems before, but now I forgot all of them. Let's do it. Cheer up. So, we are going to have a stack of stacks, and each stack will have the same capacity, and we can pop a stack at a specific position. Also, we can pop the last stack, right? I think that captures the meaning of this problem, and what we are going to do is to record the size of the stacks, right? Let's say we have size 3, 4. Actually, let's make it more realistic. 3, 5, 4, 7, right? And we are going to, this is stack 0, stack 1, stack 2, stack 3. And we are going to have, how about make this two the same size. So for size 3, we have 0 and 2. For size 5, we have 1. size 7 we have 3, and we know the size of each stack. So that we can find the stack which we are going to push the dish, right? We only need to know the stacks which are not full, right? I think that is the case. So forget about this. And we're going to have 2 sets of stacks. One set is full, one set is not full. And if we pop one stack from a full stack, we are going to insert that stack into the not full set, and we will keep it as a sorted set, and we can easily retrieve the smallest index from this set to push the dish into, right? And that's how we implement push. The time complexity is, let me see, 1, right? Because it only need to retrieve the smallest index of those columns in the not full set. This is a push. What about pop? Easy. We get the not full set. No. Let me see. We have a not full set, and we are going to also have a not empty sets, right? So we are going to retrieve the largest number of not empty sets. And the time complexity is also 1. And if we pop a element from a not empty set, that means that set, that column, that stack might become empty. So we might need to remove that one from the not empty set. That can be done in 1, right? Because we just remove the last one, right? And since we are going to push a dish into a stack, that means we might create a new not empty set by using this operation. So this is not O1 anymore, it is O log n, right? And what about puppet stack? So when we pop a dish from a specific stack, we are going to find that stack in the not full set. So if it is in not full set, then we are going to pop one dish from it. And if it becomes 0, then we don't do anything. If that stack is in not empty stack and we pop one dish from it, we might need to remove it from not empty because that stack might become empty, right? Okay, that's it. So, okay, we're going to use set and discuss 2 solutions. Yeah, exactly what we analyzed here. The push is log n. The pop at stack is also log n, right? No full stacks. Not full stacks. And we also keep a not empty stack. Okay, I think that's it. That's how we solve this problem. Oh, hard days, man. I want to play some basketball. Okay, I'll do some exercise now. I'll see you guys later, alright?